In this video, I want to take a quick look at an introduction to three dimensions. If you've never seen three-dimensional coordinate system before, well, here we go. I'm hoping you're at least used to our usual two-dimensional coordinate system where you have an x and a y-axis, and each point in the plane is given coordinates, being the x-coordinate and the y-coordinate. Now we need to add a third axis. We want to describe space. Now, one of the problems I have is that I'm drawing on a flat thing. I'm drawing on a plane, and I'm trying to describe third dimension. So technically, I need another axis that sticks straight out at you, coming straight up off the screen and straight into the screen. However, that's kind of hard to draw. So I typically draw it, on a slant here, and going backwards there. This is going to be now the z-axis, and there's two ways that I could now label this. I could put the positive z-axis coming out this way, which I'm thinking of is coming up out of the screen, or it could do that way, which would be going into the screen. I am going to put it here, and this is what is called, this is the positive z-axis. This is what now will be called a right-handed coordinate system. Right? Notice the way we determine whether it's right-handed or left-handed is if you start, I'm going to take my hand here, my right hand, I'm going to place it so that my fingers are in the direction of the positive x-axis, and it's going to roll to the direction of the positive y-axis, and then, so here, can I do this positive x-axis to the positive y-axis? It's coming straight out, coming towards me. Right. I think things are perhaps turned around, comes out at me. If I tried to do that with my left hand, by being able to roll through the small angle from x to y, I gotta get my hand turned around, and so I have to go upwards. Right? Maybe this is better. Here we go, from the positive x to the positive y direction, and you can see this is pointing into the screen. Right? Although it looks funny, I'm watching myself in the video. It's coming out of the screen. Everything's reversed. So this is the tricky part, right? This is what I would call a right-handed coordinate system. Typically, I don't draw the right-handed coordinate system that way, because typically I would want the z-axis pointing upwards. So I would draw it like this, and I would say x, y, z. So rolling from the x direction to the y direction, the z goes up, right? As I turn my fingers from this to that, my thumb is pointing in that direction. Right? Left-handed coordinate system would just swap any two of those, right? In this one, if I had done x, y, and the positive z was the part going back that way, then that would be a left-handed coordinate system. Now, plotting points, rather than having two coordinates, you have three coordinates. So, for instance, if I said move this far a in the x direction, and then move that far b in the y direction, and then go up this far c in the z direction, then that point is the point, come on now, that's the point a, comma b, comma c. Trying to draw 3D is tricky. I don't think thinking about 3D is really that hard. We live in a 3D world, and we navigate it all the time. But trying to draw pictures of it, you're trying to render it in two dimensions. And there's just different things that happen here. For instance, if I were to draw my coordinate system and then give you a point here, do you have any idea where that point is? The answer is, I'm going to draw several pictures that show you have no idea where that point is, because I could, like this one, I could say, oh, drop a perpendicular down to the xy plane, and then you can mark off, what I'm trying to do is I'm trying to draw line segments here that are parallel to the different axes. So this vertical one is parallel to the z-axis. This is parallel to the x-axis. This is x, y, and z. Right, and this is parallel to the y-axis on this side. It locates that point reasonably well. But at the same time, I could have done this. So let's draw my axes in here, get this point in a similar spot, and say, okay, here's the negative z-axis sticking out that, negative x-axis, x, y, z. And I'm now going to say, okay, this drops down perpendicular, whoops, what just happened? This drops down perpendicular right to here, and then I've got that and that. So where this one looks like this might have a positive x-coordinate, a positive y-coordinate, a positive z-coordinate, over here it looks like I have a negative x-coordinate, positive y-coordinate, positive z-coordinate. But I could also do something like this, draw it right there. Here's that axis going out that way. I could say, well, this comes up to here, and then I can drop those there and there. Oops, that one didn't go really in the right direction. That this now looks like it has a negative z coordinate, and a negative x coordinate, and a negative y coordinate, right? That just drawing the dot in there doesn't really tell you where it is. That just becomes tricky. The thing is, I'm going to hold my pen up here in front of me, right? The pen is a line segment, but if I orient it in just the right way, it looks like a point, right? Just a single point. And so any point on that line segment would look to you like it's in the same place. You wouldn't be able to tell how far along the line it is. So when I'm looking at this picture here, and this picture here, and that picture there, it's like I'm just seeing 3 points that are all in the same line that's lined up in whatever my viewing angle is, right? And I can't tell the difference between one of the points and the other unless I have some sort of guides to help me see where they are. And so quite often when I'm drawing pictures, I'm going to be putting those guides in so you can see what's going on, right? Later on in the course, when we get, we start doing functions of several variables, I'm going to draw the graph of a function. I'm going to put this thing up like that, and it's going to be a surface. It's like, well, where the heck is that surface? Well, until I drop down into the plane here, and here, and here, and here, to say where that surface is over, it's really hard to tell exactly where it is. So we'll be drawing those kinds of references all the time. And although I'm trying to do it fast, I'm reasonably careful that I'm trying to stay parallel to the axes to get a better sense of what is parallel and what direction I'm moving in. Okay. If you have access to some sort of 3D software, you might be able to see this, with a little bit of motion, and I find it easier to see what's going on if I can move it around a little bit. So what I have here is a right-handed coordinate system. So at the moment, I've got the positive x-axis running off this way, positive y-axis is here, and the positive z-axis is going upwards. That is a right-handed coordinate system. Now, I can plot a point here, right? Let's plot the point 1, -2, 1. Right? You have any idea where that is? Well, there's certain things I can do if I get the xy plane here in a spot where it looks really just like a line. I can perhaps see the z coordinate of that thing being up at about 1, right? This is 2, so that's probably 1. If I look straight down the z-axis, then I can perhaps see that, what direction here? This is the y direction down to -2, and the x direction is a positive in this direction. So it looks like the x coordinate is 1, the y coordinate is -2, and we already saw the z coordinate was 1, which is what we typed in. But just trying to draw it becomes tricky. Having some sort of software to help you visualize it really is quite useful. Now, I want to talk a little bit about some equations, just some basic equations here. Probably the simplest equation is just one of the variables equals a constant. What does x equal 3? When we talk about equations, let me go back over here for a minute. If I'm in the plane, just your plain old xy, and I say, what does x equals 2 look like? Right? To say the graph of an equation, you're saying, give me all the points in the plane whose coordinates satisfy this equation. Well, the thing is, there's nothing about y in this thing. So all I have to do is make sure that the x coordinate is 2, and then y can be anything it wants. So you've got this whole line here at x equals 2, and y then can be anything. Any point on this line, 2, 1, 2, 2, 2, 3, 2, 7.5, whatever, the x coordinate is 2. Satisfies the equation, it's on the graph, right? The graph contains that point. But when you go to 3D, what's happening? Right? So let's pop back over here. If I were to say I want x equals 2, this is now showing me a big old plane. Right? move 2 out in the x direction. There's no y and z in this equation, so they can be anything you want. Any point on this plane, this is the point 2, 1, 1. Here's the point 2, 1, 2, or 2, 0, 0, or 2, 2, 0, right? Every single point on this plane has an x-coordinate of 2 and a y and z coordinates of whatever the heck you want. Right? Each point, though, satisfies that equation. Right? And you see this plane. I'm going to switch it just a little bit because I'm going to get it to go through that point. So if I look at the equation x equals 1, then it's passing through that point. Likewise, if I looked at the equation y equals, let's say, -2, then I've got another plane. Right? That plane is one that goes that way. And let's throw one more in just for good measure here. How about z equals 1? And so each one of those planes is passing through that point that we had. I don't even know if I can see the point anymore. But well, I guess you can kind of see it in that angle. Yeah. This is interesting to me as I look at it because it feels like the perspective is all wrong, right? This edge out here is what's actually closest to me, but it looks like it's shorter than the stuff in the back. Actually, it's not shorter than the stuff at the back. My eyes are playing a trick on me. That this edge is actually parallel to this edge, and the front and the back are the same length. Except that I'm used to looking at 3D, and I'm used to seeing perspective. At the moment, I have this set to draw at an infinitely distant lens, right? And so it's keeping parallel lines parallel. If I want to see it more like I'm used to seeing it, I need to go for like a wide-angle lens. And I'm going to back up a little bit here. Now, as I look at this thing, I start getting more perspective. I want to get rid of one of these. Let's get rid of the y equals so I can see something here. Let me get rid of this. So yeah, that looks more like what I'm expecting. The stuff in front looks bigger than the stuff in the back. Okay. Again, it's a matter of how am I drawing a 3D thing in a 2D space. Right? It's really hard to tell when it's just static. One of the things I like about the software is, well, among other things, you can change the point of view, for instance, or you can change the perspective. But you can also, move it around a little bit and be able to see it in motion, which I think helps us say what's in front and what's in back. Yeah, so there's basic, very simple equations, planes. I should point out that the special planes, for instance, when x equals 0, I would call that the x equals 0 is what I would call the yz plane. In fact, I think I've already mentioned the xy plane. The xy plane would be when z is equal to 0. That's just the coordinate plane down there. All the z coordinates are equal to 0, x and y are anything you want. And of course there's one more coordinate plane, which would be y equals 0, and that would be the xz plane. You're fixing y to be 0, you're letting x and z be anything you want, so that's what's called the xz plane. And those 3 coordinate planes divide space up into 8 regions, 4 of them up above here, and then 4 of them down below here. Right? Just like our 2D coordinate system, the 2 axes cut the space into the plane into 4 regions. We call them quadrants, right? Here in space, we would have 8 octants. Now, in the plane, we have quadrants 1, 2, 3, and 4, right? That's the way we're used to doing them. But in space, we have 8 octants. And I will admit to you that I have never seen them ordered. The one, I don't know which way is positive or negative, but let's just say this is positive x, positive y, positive z. So this octant right up here is what I would call the first octant because it has all positive x, y's, and z's. And then how you count the other ones, I've never seen a consistent way of doing that. In fact, I don't think I've ever seen anyone try to do it. This is the first octant, and then there's all the other 7 octants. I think that's enough.